Good morning, dear students. Uh, Welcome to this class on prestressed concrete. Uh, Last session we have completed uh, half of the Unit 2 syllabus, where pre-stressing systems we have talked about. There are two systems. One is a pre-tensioning system and a post-tensioning system. So pre-tensioning system and post-tensioning system is completely discussed in detail till the last session. This session we'll talk about the rest of the syllabus of Unit 2, nothing but analysis of pre-stress. Okay, so let us see what are all topics you have in this analysis of pre-stress. So we'll just talk about basic assumptions first. Then we will see how to calculate the stress at a section in a pre-stressed concrete section, and the resultant of that stress, because you will have different types of stresses at a section. So we'll finally need the resultant value. Then we'll go for pressure line concept of finding the stresses. Then we'll talk one more concept of load balancing, and then we'll talk about stresses in tendons also, not only the concrete, but also in tendons. You know, because the reason why we talk about stress in tendon, because stress in tendon is visualized in the maybe pressure gauge or so, because the hydraulic jack itself will show you the stress in tendon. Then you may think that what is the need for stresses in tendon, as once the re-stressing, the jacking operation is done, uh, at a later point of time, where the concrete is going to take that stress, and the deformations in concrete are going to change the stress in tendon. That is what is this one. And the cracking moment we'll talk about the stress in concrete, where the once the tensile stress, uh, the amount of tensile stress developed in concrete is equal to the cracking stress. So that to create such environment, how much moment is required. So this is the second half of this unit 2 to talk about. So it is uh, the purely calculation based content. So you need to solve some problems to calculate stresses and all using these different concepts. Like first one is a very basic fundamental concept of finding stresses, just like the overlapping of stresses um, from one type of stress to other type of stress. The second one is pressure line concept. The third one is load balancing concept. Okay, so this is what we talk about in this uh, unit 2, the second half of the unit 2. Okay, so let us talk about assumptions. They are very regular, because the concrete, whatever we have assumed, even for reinforced cement concrete, the same holds good for pre-stressed concrete also. Okay, that means the concrete material, though it consists of cement, fine aggregate, coarse aggregate, water, and also some mineral admixtures, maybe chemical admixtures. Likewise, it is a mixture of so many materials, but still we take concrete as a single unit and we assume that it is a homogeneous made of same material at all places. Isotropic, having similar properties in all directions, and it is elastic material, which means if you remove the load it comes back to its original position. Okay, so this assumption you know very well, and also already had this assumption for reinforced cement concrete analysis also. The analysis and design of the regular reinforced cement concrete also we have used a similar assumption where the material is elastic, which means you load the material, remove the load, and it comes back to its original position. Okay, and isotropy means different directions the properties are same. For example, Young's modulus in x direction, Young's modulus in y direction, Young's modulus in z direction. Okay, right. So in any direction, the property of the material, whatever property you take, maybe Young's modulus or maybe Poisson's ratio, whatever property you take, that will be same in all directions. Okay, not only these three, in any direction the properties are same. That is what is called isotropic material. Okay, homogeneous material means the material is same at each and every location in a member. That is called homogeneous uh, member. Okay, so property of homogeneity means you take any location, this location or this location or this location, any location, the same material shall exist. Okay, but in actual sense it is not so, because at one location you find coarse aggregate, at one location you find fine aggregate, at one location you find a paste, water cement paste, at one location you find a cavity like a void, okay, air void, some location you find water droplet, something like that. So it is different at different locations, but still we assume that the concrete is homogeneous. Okay, so this is to have a simplicity in calculations. Uh, uh, we need to have these assumptions. So concrete is assumed as homogeneous, isotropic, and elastic. Okay, right. Within the range of working stresses, both concrete and steel behave elastically is the another assumption we are making. So within the range of working stresses, the stresses that are coming onto the members, concrete members, okay, they are called working stresses. So all those working stresses uh, upon concrete and steel, so they behave elastically. Already it is mentioned in assumption 1 that concrete is elastic. Steel is also assumed in the similar manner. Okay, and steel you don't need to tell about the homogeneity and isotropic, because it is isotropic and homogeneous. Okay, because it is factory made material, right? And this assumption, this also, like plane sections remain plane even after bending. Okay, so this assumption is already used by you when analysis and the design of reinforced cement concrete. So this will give you the basis for assuming the strain is proportional across the section. That is what is the use of this assumption. The plane sections remain plane is the basis for the strain to be proportional across the cross section. This is what the diagrammatic representation for that. So this also you have used in your RCC. The same assumption holds good for PSC also. Okay, right. The other one is like as long as tensile stresses do not exceed the limit of modulus of rupture of concrete, that means visible cracks. Any change in the loading of the member results in change of stress in concrete only, which means the tensile stress in the steel, whatever is imparted by the jacking operation, whatever is operated at the time of jacking, that means pulling of the tendon, the same stress will be maintained. That is the assumption. So that means, in a simple way, the change in the stress in steel is negligible and is not considered in the computations. Okay, so we assume that whatever value you have seen while jacking the, the hydraulic jack, while pulling the tendon, the same value is taken without any changes, though there will be minor changes in the value, but we will neglect all those changes in the stress of steel. Okay, so that is the other assumption, right? So these are the assumptions before we start analyzing this pre-stressed concrete members. Okay, right. Let us start with a simple case where the pre-stressed concrete is having a concentric tendon. Okay, and before that, the notations and sign conventions you must be aware of, as you have to work out with the notations, not with them with their names, right? So stresses due to pre-stressing alone are generally combined stresses. So those combined stresses will be just like your the columns where we have both axial and bending. The same similar manner, we will analyze the pre-stressed concrete members also. Okay. So the notations that you can see clearly to understand what each notation will tell you about. So capital P denotes pre-stressing force. It is positive when you produce direct compression. Okay, when it produces the direct compression in the concrete, that is what is meant by pre-stressing force. Small e denotes eccentricity of pre-stressing force, okay, which is measured from the CG of the concrete cross section. So for example, if this is the CG of the section, and if your duct is provided here, so the distance from CG of concrete to the duct, CG of the duct, is taken as eccentricity E. Okay. If you have multiple levels of pre-stressing tendons kept, so for example, one more duct somewhere here, one more duct somewhere here. If you have such distributed ducts, as you have seen in the example of preparing a post-tensioned box girder, you have seen there are so many locations for ducts. So in such case, you have to work out a common location. That means CG of tendons also, instead of just single location. If you have multiple locations of tendons kept in the member, you have to work for Cg of steel. So Cg of concrete, Cg of steel. So the distance between them is eccentricity. Okay, so that is small e value, and the moment is calculated. Moment developed by the pre-stressing force P into E. It's very simple. Force pre-stressing force multiplied by the eccentricity value. And capital A, cross-sectional area of the concrete member, something like this. And capital I, moment of inertia about the centroid, and ZT, nothing but the section modulus values, top and bottom, top and bottom fibers. Okay, and F superior and F inferior given by the notation. We are following the notations from your prescribed textbook, which is N. Krishnaraju. So superior in the sense top, stress at top, inferior in the sense stress at bottom. Okay, so the stresses at top and bottom. F SUP is the stress at top. F I N F is the stress at bottom. Okay, so the stresses at extreme fibers need to be found out, and YT, YB distances of centroid from top and bottom fibers. And small I here is the radius of gyration, which is nothing but you know it very well from your mechanics, square root of I by A, radius of gyration. Okay, so this is the term you come across while you solve for moment of inertia. Okay, so that is what is radius of gyration, square root of I by A, right? So these are the notations that are to be uh, remembered while solving the problems on pre-stressed concrete. Okay, right. Taking concentric tendons case where uh, tendon or duct is provided in the exactly at CG of concrete section, as you see it here. So this is the location for tendon to place, and the stress is direct stress and it is compressive. Is P by A. It's very simple to calculate the direct stresses, direct compression. So compressive stresses are taken as positive, as you have seen the notations that we have mentioned. Okay, right. So this is about the concentric tendons. Okay, right. We'll see the rest of the things in the next session. So this session is mainly to introduce you the analysis of pre-stress topics, what topics we are going to discuss in this unit 2, and what are all the assumptions we have made to analyze the pre-stressed concrete members. So they're very simple and majorly well known to you. Materials are homogeneous, isotropic, and elastic, both steel and concrete. Plane sections remain plane, the second one. The third one, the any changes in stress of steel is negligible. Okay, throughout this analysis part. Okay, so this is about the assumptions made, and the notations that we are going to use, the sign conventions, concentric tendons, if at all they are there, how you analyze them, how you get stress in the concrete because of concentric tendon. It's like an axially loaded member. The stress is direct stress and this direct compression. Okay, right. Thank you.